cut off through.
It works out like that. Voltage divided by, which is the predominant arrangement for the active region. Yeah, it's most often used if we operate the transistor in the active region. Now, the problem we have, of course, is that transistors are very susceptible to temperature change, right? So if the temperature goes up, beta goes up, and it moves the transistor towards saturation, or the amplifier towards saturation. And if the resistance goes down, it moves it toward cutoff. I mean, if the temperature goes down. So what we do is we come in and we establish a beta. And this guy right here, this is the temperature compensating resistor right there. So what happens if we clamp the base at a certain voltage, and here what would that voltage be? So we just come up here and do what? Just use the voltage divider formula real fast, right? So what, that would come up here and go, this is the guy that's setting the bias on the base right here. So all we're going to do is to calculate VB, all we do is calculate the voltage drop across that resistor. Yeah, so we'd say 10K over 110K, right? So VB would be equal to the resistor we wanted across divided by the sum of the two. They're both K, so the first thing I do is just drop the K, right? Okay, and I can mark that off right there, and it's going to be about 1/11. And then we multiply this times 20, and this should give us VB. $1.81. So relative to common. Now what this does is it clamps the base at a voltage, right? And if it clamps the base at a voltage, then it's going to clamp the emitter at a voltage, and now the temperature can't change it, right? So we'll, instead of 1.81, we'll just use 1.8. So that will set this right here at 1.1 volt, right? So VE, all we do is take VB, and then we subtract what type of transistor it is, and the predominant transistors is silicon, you know. And this gives us approximately, so VE would be equal to 1.8 minus 0.7, which would give us 1.1 volt. So now if this tries to change, so if it tries to go up, it can't go up because of the 0.7 of a volt. If it tries to go down with temperature, it can't go up because it's got this guy right here has got to set at 1.7 volts. Now what it allows us to do is we're going to bring an AC signal into this thing. And right now we'll play around with sine waves because it's real easy to figure out. And we'll set this up on electronic workbench so we can actually see it operate. But what we do is we have this capacitor. So these two capacitors right here are called coupling capacitors. And what it does, it allows us to bring AC in, and then the AC can add to or subtract from the base. And it allows us to get AC out and not affect the bias voltage, right? So let's go ahead and figure out where we're setting this guy here. So first of all, we need to calculate IE. So IE would be equal to 1.1 divided by 1K, which is going to give us 1.1 milliamp. Right, I like that on the. So 1K resistors is 1 milliamp per volt. Are we okay? Yeah. What's nice about a 1K resistor? And also so 1K resistor is 1 millivolt per volt. So if I got 1.1 volt, that's going to be 1.1 milliamp. 10K would be 100 microamps. So I take that and I come up here and I run this through VRC. So VRC would be equal to 1.1 milli times 10K, which would give us 11 volts, right? Okay. So VC, what would VC be equal to? Well, here we're going to use Kirchhoff's law. We're going to say VC would be equal to VCC minus 11. Because this is where we're measuring this, right? So this is VC right here. So what would that give us? 9 volts. So VC, so what we have is VC is sitting up there. And it's going to equal to 9 volts. So okay so far. So this guy is biased and ready to operate. So what I can do is I can come up here and I can apply an input voltage. And it's got to be, can't be greater than 0.8 or it cause it to go in saturation. Can't be less than that. I'm sorry, or it'll cause it to go in cutoff. So let's bring 200 millivolts peak to peak. So this is going to be VN. And I'm not going to do that in RMS, but this is going to be volts peak to peak. So we're bringing in AC here. So it means it's going up 100 millivolts. And it's going down 100 millivolts. That makes sense? We're okay? Okay, Jobber? So what happens is when it goes up 100 millivolts, it's going to add to this. And when it goes down 100 millivolts, it's going to subtract from this. So let's do the plus first. So the plus, then my base voltage. So what I'm doing is I'm changing the base voltage. If I change the base voltage, then that's going to let the emitter voltage change, right? From the AC signal. It's sitting here biased, it can't change because we're locking it at 1.8. So this guy is the temperature stabilizing resistor. And what we mean by that is it's going to do what? It's going to keep this thing locked at a beta even if the temperature goes up or the temperature goes down over a certain range. So VB max would be equal to 1.8 plus 0.2. ID minimum would be equal to 1.8 minus 0.2. So what would this go to? I gave it to you. Oh, it's 0.1, I'm sorry. Thank you. Let's do 200 millivolts anyway. So we'll see the change. In fact, let's do 500 millivolts because I really want this thing. I really want y'all to see the change and figure out what's going on. So let's change this to since we haven't done the calculation, it'll be okay. In fact, let's do 1 volt peak peak. So that'll be 500 millivolts up and 500 millivolts down. We can do that without saturating. Because the other way we wouldn't see a big change. So when it's going to go up on the input, so that'll give us 500 millivolts up and 500 millivolts down. So when we calculate our maximum voltage, well, what we'll do is we'll add 0.5 to these and see what happens. So what would the input voltage go up to? Yeah, so 2.3 maximum. And then what would the minimum voltage be? Yeah, 1.3. Okay. So what's going to happen is it's going to come up here, and let's come over here and erase some of this math over here. So we're going to have room to do this. So one important thing we did do out, we need to calculate VCE to determine whether the transistor is operating in the active or the. So I'm going to take VCE would be equal to the voltage right here, which is 9. Sorry, would be 9 minus 1.1. 7.9, right? So is it in the active region? Is it in the cutoff, or is it in saturation? If it was cut off, it would equal to 20 volts, right? You understand? If it's saturated, it'd be less than a volt. So this guy here is operating in the active region. This is where it needs to be.
Is it cut off, so it'll have less than a volt?
No, if it's in cutoff, it acts like an open switch. It's a series circuit, an open switch and a series circuit. What happens to an open device in a series circuit? The entire voltage appears across it. So if this equals to 20 volts, then the transistor is cut off. If it's less than a volt, we consider the transistor to be saturated. If it's somewhere between 1 volt and VCC, then we consider it in the active region. So right now, this guy would be operating towards saturation. And why is that important to know? Because that'll show us which side clips first. So what we would like it to be is we would like this voltage right here to be what? We'd like it to be 10. Now why can't we get it at 10? Because we're stuck with standard resistors, right? You understand? So like I said, an engineer could pay $5 for a 1K rheostat, or they could pay 15 cents for a 1K 5% resistor. What are they going to do? Yeah, they're going to save money, right? You understand? So what we do is we get this thing as close as we can, and we're not going to teach design in here because there's a little to it, even though we used to. That's what you consider. You calculate the resistors perfect, and then you choose the best standard value you can get, right? You understand? And then you screw around with it. So if it doesn't come up exactly, you would say, well, let's come up here and put a smaller resistor down here and see how it works. And then and that's the design of transistors. So you design it with math, then you choose standard resistors, and then you tweak it. And then once you got it, then of course, you realize that every circuit is not going to be exactly the same, and you make sure when you set up the specifications, it works within the tolerance of all your devices. So your amplifier might get a little bit out than the next person, right? So that means I might rate my amplifier at 50 watts, but sometimes it might give me what? It might give me 75. Sometimes, and the worst case might be, 60. Well, I would rate it at 50, which means what? That would make sure my amplifier gives me what everybody expects out of it. So when we mean amplifier, what are we trying to amplify? We can't amplify resistors, right? So what are we trying to amplify? Power. We don't call these things amplifiers. We call them power amplifiers, right? Why? Because we're trying to get more power out than we're. Now understand, these guys are not creating power. We call that thing up there, that 20 volts, we call that the power supply. So the power supply is not only having to provide power to the amplifier, it's also trying to give us a power gain from our what? From our input to output. So some people are a misconception that a power amplifier creates power. It cannot create power, right? Y'all understand? All it can do is change its form. So the ultimate goal of an amplifier is to get power gain. Period. Now we can get power gain by getting a voltage gain, right? Or we can get a power amp. We can get it by getting a current gain, or we can get a power gain if we somehow get both of those. But understand, the guy is not creating a power gain. I mean, it can get more out than we put in, but we'll never, ever, ever, ever even get close to that, right? You understand that? Because of the efficiency of the amplifier. So that 20 volt CC, that is the power gain. That is the power supply. It's the guy that's providing the current. It's the guy that's providing the voltage. It's the guy that's providing the power. So if I design an amplifier and I don't get a power gain, that means I'm getting less out than I put in, and I wouldn't be in business very long, right? So what we'll figure out here is what type of gains do we get to come up and get the power. Of course, power, we got several formulas. What's our formula for power? Our main one is what? V times I, and then we can rearrange that. So power would be equal to I squared R, or power would be equal to V squared over R. Those are our three main power formulas. But they all come from this guy right here. Y'all understand? Okay. So what we're trying to do is we're either trying to, if the input resistance to the amplifier and the output resistance was the same, then if we got a voltage gain, we would get a what? We would get a power gain. But what we'll do in a minute is we'll try to figure out what the signal sees as far as the opposition it sees, and then we'll see what's going on. Everybody okay? So we know this guy's operating in the active region because VCE is equal to somewhere between what? 1 and VCC. Everybody okay? That makes sense. Okay. So what we would do is when this input goes up to 2.3 volts, then my emitter voltage, then my VE is going to go up to, now we've already taken out the 7/10. The 7/10 was taken out by bias. So what's going to cause this to do, the voltage on this resistor right here is going to go up to what? (1.1) plus 0.5. So it's going to go up to what? 1.6 volts. All right, you okay? That makes sense? Yes or no? So this voltage right here is going to be 7/10 of a difference between the base and the emitter, but we've already taken out the 7/10 of a volt when we came over here and said 1.8 and 1.1. So you don't keep taking it out, right? You understand? So what that means is, if this input goes up to 500 millivolts, that voltage on that emitter resistor goes up 500 millivolts.
1.8, you add that plus 0.5.
No, we've already got this voltage right here. So this is going up to 2.3 volts. So I've got 2.3 volts over here. This is going to drop 7/10 of a volt, right? You understand? Which is going to cause it to go to this plus this, right? You understand? Which would be 1.6 volts. So we don't have to redo the math over here. Once I've got that, once this goes up to a certain voltage, my emitter goes up the same amount. Okay, that makes sense. So IE will go up to 1K, 1.6 divided by 1K. So it's going to go up to 1.6 milliamps. Y'all follow that so far? Now this is the positive voltage. So what's going to happen is I've got more current here, so it means this resistor up here is going to drop more voltage. So what I would do is I would come up here and say VRC would be equal to 10K times 1.6 milliamps. So it's going to drop to 16 volts. That means VC is going to drop down. So VC is equal to VCC minus VRC. So my VC is going to be equal to 20 minus 16. So it's going to drop down to 4 volts. So it was setting at what? What was it originally? 7.1. So it's going to drop down 4 volts. So VC is going to go from 7.1. And it's going to drop by 4 volts. So it's going to drop down to 3.1. So it's going to go down. And that's going to be the peak. You understand this? So what happened is this guy went down to what? So it's sitting at 7. It dropped down by 3.1 volts. Right? That makes sense? So I put 500 millivolts in. Now, what happens, guys, is that we're taking our output across the transistor. So what happens on this amplifier is that if the transistor cuts on more, so if the input voltage goes up, the transistor cuts on more and the output voltage goes down. So one of the characteristics of this one is that your output voltage and your input voltage are going to be 180 degrees out of phase. We're okay so far? You better lost. What?
The 10, okay, the top, yeah, VRC 10 times 1.6.
Now, originally what it was, originally when we came over here, before y'all came in, guys. So y'all making us drop back, right? Originally what we had was, we had 1.1 volts dropped across here. So what we had is, this is what we started out with. So originally we had 1.1 volts, right? This was our VE to start off with. And so we started off when we said IE would be equal to 1.1 divided by 1K, which would originally give us 1.1 milliamps. And then we said VRC would be equal to, voltage drop across that resistor would equal to 10K times 1.1, because what we're doing is we're assuming that IE and IC are equal to each other. Are they equal to each other? No, but they're so dang close. Dealing with the tolerance of the resistors, they're close enough to give us a very good calculation, right? You know. So that guy means it would drop, how many volts? 11 volts, right? That makes sense? Okay. So, VC, where did we come up with 7.1 at, guys? Oh, so I did something wrong up here, so I see that. So VC would be equal to, VC would be equal to 20 volts minus 11 volts, which would give us 9 volts. So I messed up here. Yeah, it's going to be sitting at 9 volts. If we measure this, it's going to be sitting at 9 volts. What we'll do, let's just to do this, I'm going to keep all this stuff. And then I'm going to go, I'm going to remote in. Hopefully nobody's using it over there. I got a sign on the computer. So, y'all write this down. We got 100K, we got 10K, we got 10K on our base, 10K on our collector, and 1K. So what I'm going to do is I'm going to remote into our computer over there that's got electronic workbench on it. And we're going to build this amplifier. Okay, we got it? So here's an amplifier already here, guys. So what I'm going to do is I'm going to just come over here and just change these values, if it lets me. So this is 100K. This is 10K. This is 10K. And this right here is 1K. And what we're going to do is we're going to turn off the scope right now. And we're going to fire this baby up. So this guy's going to measure BC. This guy, I don't have anybody measuring VB. Oh, this guy's going to measure VB, right? See that? This guy's going to measure this current. This guy's going to measure our base current. So we could actually see the beta of the circuit, but that's okay. Okay, let me disconnect this guy. I think it's affects. Let's just go ahead and delete it out of the picture. And right now we have no input and we have no output. This was supposed to be 9 volts, right? Okay, the voltage is wrong. There we go, thank you. One little minor change. Okay, 1.7, right, 9.2. So even though our calculations, see, it's a little off, but that's okay. 1.8 is fine, right? You understand that? This is why we don't carry these things out real far. Usually we round these to 1 decimal. So here's our voltage. Okay. So here we calculated 1.1. So our voltage is a little off, but it's really, really, really close, right? Understand? So what we're going to do is we're going to come in and we're going to bring in an input signal. And what's neat, guys, is when we superimpose DC on top of AC. So let me pop a new slide in here. If everything's working with the transistor the way we should, if it's not saturating or cutting it off, then what happens is we're coming over here and we're allowing us to set a DC voltage. Which we have about 1.8 volts right there, right? You understand that? Okay. And what we're doing is it's allowing us to bring a DC voltage in right here. We'll talk about how to put these polarized capacitors in there. And what it's letting us do is letting us bring an AC voltage in over here. So one of the main things we talk about, what does a capacitor do for us? It blocks DC and passes AC. Now the amount of AC it passes, you'll learn that later on, would be dependent on frequencies. But we're going to choose a capacitor that's big enough so the frequency don't matter. So what it allows us to do, it allows us to have 0.8 volts of DC right here. And what happens is when this goes up, it adds to that voltage. And when it goes down, it subtracts from that voltage. 1.8, yeah. So what happens is we end up with our base current doing this. So it's going to be a mirror image of what we're bringing in. But it's going to be riding on top of DC. Now, when we measured this, to start off with, I had DC, and that DC was setting at 1.8 volts. Now, what would it measure when I superimpose that AC signal there? If I measure it with a DC meter, a voltmeter, DC voltmeter. Well, it's going to average it. So what's the DC average of an AC sine wave? What's the DC average of an AC sine wave? What's the DC average of an AC sine wave? 0. We proved that. So what that means is if this is a sine wave coming here, my meter is going to average that right down the center. So what that means is that even though if I put an AC sine wave on that thing, your meter's still going to measure the correct bias. Because your DC meter is going to average that sucker right down the center, right? Even if it's sound and it's doing this, it's still going to average it right down the center. So on sound, this guy right here, even though it's all over the place, is going to equal that down there, right? So even though so what we got on sound is we've got all these different frequencies superimposed on top of each other. But your positive is still going to be a mirror image of your negative, right? You understand? And your DC meter is going to average this out. So what we can do is we can check our bias even if the amplifier is active. Because what's going to happen? And if your bias is screwed up, then that means something's going on. And we'll look at what's going to cause the bias when we accidentally saturate this thing or we accidentally cut it off. So I can come over here. I'm going to put a sine wave in on this thing, and we'll see the DC bias. It'll change a little bit, but it's not going to change much to square around with our calculation. So we'll come up here and bring in a function generator. Now normally to troubleshoot these things, audio is all over the place. So to troubleshoot these things, normally we bring in a known waveform. If I bring in a known waveform, then I know what to expect out, right? You understand? So most people that troubleshoot these things have these function generators that they can actually put a sine wave in, and they know what to expect. Now we have to figure out what this thing does. I can't remember if it's RMS or what. We set the output voltage. So we'll come over here and we'll hit this right here. And then what we'll do is we'll put a 1K signal into it. And it's a sine wave. 50% duty cycle means it's going to be a sine wave. Amplitude I have is 1 volt. So we'll measure and see what it says. So we're okay so far? So we'll fire this guy up. And notice the bias stays about what? About 1.7 volts. The output stays about 1 volt, about 10 volts in fact. Let's lower this down a little bit. Okay, so see the bias stayed about the same even though it's got an active signal coming into it, which is pretty. So what I'm going to do is, and we'll look at this in a minute, I'm going to take my oscilloscope, and we've got a 2-channel oscilloscope, and I might have to slow it down. This oscilloscope is not very good. The simulated oscilloscope. Oh, we got it on 1 hertz. This is 1 kilohertz. So I have both of my inputs and outputs. So my input is set. So I've got my input hooked up to channel 1. And then I got my output hooked up to channel 2. And I don't know if I can shift this anymore, guys. This guy don't have a really good range on actually setting the position. Come on, come on, come on, come on, come on. Come on, come on. So what I have here is I have my input set on 1 volt per division. And I need to change where I hook up my scope. I'll show y'all in a minute. So I'm putting in 1 volt peak to peak, and I'm getting out 2, 4, I can't see the minor divisions.
Can you take it out in your account?
Yeah, we'll try. We'll come up here and try to. Usually the scope goes out of sync. So yeah, it's working really well. We can't see the top real well. This is as far as I can shift it, and I can show y'all, because what we have is, this is riding on top of DC, right? You understand that? So what I'm doing is I have my scope hooked up to the base. So the signal's riding on top of 1.73 volts, right? You understand? And then I've got my output hooked up across the collector, so this is riding on top of 9 volts. And this scope only gives me a certain amount of shift. But what we see here is that I have my input signals on the bottom, my output signals on the top. So roughly my input, I'm bringing in about 1 volt peak to peak, right? It's like my 2 volt peak to peak, sorry. And my output is on 2 volts per division. So I'm getting out 2, 4, 6, 8 over 8 volts. Now how are we doing that? So we're getting more voltage out than we're putting in. Now this guy's not creating voltage. What's it doing? It's controlling this 20 volt power supply is what it's doing. So what we're doing is we're bringing this in to a certain amount of resistance. So what I'm going to do is, to get this, guys, I'm going to show you the purpose of the coupling capacitor. So what I'm going to do is I'm going to come over here and I'm going to put a capacitor right here. And we'll make it a pretty good size so it's not going to affect our frequency. And then over here, I'm going to bring my scope now. And I'm going to move it from here. Oops. I'll move from here to here. Oh, but what else could I have done with my scope, by the way? Let's go back and look at that. So right now, my scope, my signals are riding on top of DC. So we got another option is that I can put my scope on AC coupling. When I put my scope on AC coupling, what does it do? Blocks DC. So we should be able to move this guy here up now. Let's move our so here's our output. I might have to stop the scope and see if I can freeze it. And here's our input now. And like I said, it's a crummy calculation. So notice I've got 2 volts on my output and 1 volt per division on my input, and then 2 volts per division on output. So what we're going to see is that when we come up here and we change this input current, and I'm not going to be able to rate this. This now sees this as 1 unit. So what happens when I came over here and changed this? Yeah. So this should right. So it should have DC should have went to equal to 9 minus what? So we started out with VCC equal to 9 volts, right? I don't know where the 7.1 came from. And then what we did is when we came over here and increased this to 1.6 volts, that would be 1.6 milliamps. Then we come up here and recalculated what our resistor would drop. That's 10K times 1.6 milliamps. So it's going to drop 16 volts, right? So VCC, VC would be equal to VC minus VRC, which would be 20 minus, sorry. So this is going to drop 4 more volts, right? So that's going to be 9 minus 4. So my VC would drop down to 5 volts. So it's setting at 9. So now what it did is it came down and it dropped down to 9 volts. Oh, I'm sorry, 5 volts. And this right here is what? 9. This is plus 5. So the transistor's still okay because we still have voltage to work with, right? You understand? We're going to deliberately saturate this thing in a minute and see what's going to happen. Now, what's going to happen is we can do all the calculations in the world, but if we're going to go up the same voltage, so if this causes it to drop down to 5 volts, then when I come into here and change my voltage down to 1.3 volts, guess what that's going to cause to happen? It's going to cause it to go up 4 volts. So it's going to go 9 to 13. We're still okay because how much voltage do we have to work with? Y'all can do the math if you want to. But what happens is my input signal is doing this, and my output signal is doing this. So one feature of this amplifier, and we call it a common emitter amplifier, is your input and your output is 180 degrees out of phase. Now in audio, it don't make any difference because your speakers don't look at phase. Your speakers look at current, right? You understand that? So as long as we have the same number of phase shifts as we move through our amplifier, as long as your left and right channel are still in phase with each other, then we have no problem. So if this was my left channel on my stereo and it gave me 180 degree, and I use the same amplifier on my right channel and both of them has 180 degree phase shift, then your speaker would be okay, right? It's just if you're left, so if you ever looked at a stereo, your left and right channels are going to be mirror images of each other. So whatever we have down in this one is going to be what we have in that one. So how could we have calculated the gain to start out with? So this is where your output is actually changing right here. Your input is felt across this resistor. Your output is felt across that resistor. And how do we calculate gain, guys? Out over in. So here we would use V out over V in, right? You understand? That makes sense? So what are we putting in? We're putting 1 volt peak to peak in, and we're getting what? 4 up, 5, 8 volts peak to peak out, right? Something's not working out right. Huh? No, what we're doing is this is our output right here. So we might have to do some recalculate because it's not going to work out. Something's not working out right. And this is where what gain you expect, right? You understand that? We need to know what gain we expect before we actually do the gain. So I'm expecting a gain of 10 out of this amplifier. But according to our calculations, I'm getting 8 volts peak to peak out, right? 4 up and 4 down. I'm putting 1 volt peak to peak in. So that would give us a gain of 8, right? But we've done something wrong, or I've done something wrong. Y'all didn't do anything wrong, I'm the teacher. So somewhere up in this line right here, we've made a mistake. So we're putting 1 volt peak to peak in, right? So this right here calculates to be what? 1.8. Is everybody okay there? Okay. That gives this, that makes this calculate at what? Yeah, so VB is going to be 1.8. VE is going to be equal to 1.1. IE, which we're going to assume is equal to IC, even though that's not true, right? You understand? Is going to be equal to 1.1 milliamp. Everybody okay so far? We're not redoing these calculations. Are we okay?
I know you think we're doing the calculation, but that 1.8, it came from you took 17 of a vote, right?
No, the 1.8 came from calculating this voltage divider. So what we did is we calculate, remember, VB is established across this resistor right here. So that's VB. The 1.1 came from ground.
Right.
So VB would be equal to, using the voltage divider formula, would be equal to 10K over 110K times 20. And what we can do is we can knock off this and this and this and this, right? So it's 1/11 volts. So that's where the 1.8 came from. Then what we did is VB, we did what? We just, so VB is 1.8. VE, we just came over here and subtracted 7/10 of a volt from that, and that's what gave us the 1.1, right? Then we calculated IE, which we're going to assume is equal to IC because they're so close to each other. And you saw how good the calculations worked out, right? Now, if you see on a test it says IE and IC are equal, you're going to say that's false. If I said IE and IC are approximately equal, then you'd say that's true. So watch out for that on test. Like I said, on my motor control, on my PLC test last night, we had a constant can never be changed. And it was true and false. Most of the people in the class said true.
So 110, what is 110?
Wait, where's 110 at?
We said VB equals 10K over 110. You had
What's that?
110.
Oh yeah, voltage divider formula is R. So voltage divider formula, very neat. We can, and what's nice about the voltage divider formula is we can calculate voltages in a series circuit without calculating current, because the ratio of resistors drops in a series circuit is dependent on, it's the ratio between that resistor and the rest of all the resistors in the circuit. So the formula for voltage is VRX is equal to RX over RT. That's the ratio right there. And then we just multiply, then we do what? We just multiply that by our source voltage. Now, of course, here we call our source voltage VCC because it's the collector voltage. But this is true, guys, for any series circuit. With one or more resistors. With two or more resistors. And what's nice about a transistor amplifier is you can almost usually calculate RT in your head. Right? You understand? And I can look and I can say, well, 1/11, that's going to be pretty dang close to 1/10, right? You understand? So if I put 2 volts up there, it would still calculate out to be okay. So what's nice about the voltage divider formula is you have a pretty good idea of what that voltage should be, right? You understand? So just looking at a 1/11, I knew this guy would be slightly less than what? Than 2 volts. Without even picking up a what? Without even picking up a calculator. And that does not, and the ratio does not change with whatever voltage you put on there. So this is what I was talking about in DC. You know, we want to calculate the voltage drop across R2, and I start off with 20 volts, and everybody comes up here and calculates RT. They take that and divide that into VS. They calculate current, and then they multiply by that all that resistors. And I say, okay, what would happen to the voltage drop across the 10K if I lowered the voltage to 8 volts? What would they do? They would recalculate the whole circuit. when the ratio that 10K drops will always be 1/11 of the applied voltage, period. Always. So if you knew the ratio, then you could have recalculated the circuit just like that, right? You understand that? So the voltage divider formula is a real neat formula because I can calculate voltage drops in a series circuit without having to calculate current. So I can do it with one formula instead of what? Two. So then what we need to do is calculate what this guy right here drops. So a VRC would be equal to 10K times the emitter current, which we're assuming is going to be the collector current, which is going to give us, that's for the 11 volts tank. Now that's the voltage drop across this resistor right here. That is not VC, and this is the problem we have in this class, is people use the voltage drop across VRC as VC. Now VC is measured right here. So I'm going to use a little Kirchhoff's law. So I'm going to say VC would be equal to 20 volts minus the voltage drop across that resistor right there, which would be 11 volts, which would give us 9 volts. So that's VCE. VC, right? Y'all understand? We okay. Then we need to calculate voltage collector to emitter because this tells us what region the transistor is operating in. So I'm going to come up here and I'm going to take what I have left over right there, which is 9. I'm going to minus that what we have there. That's 1.1. And that would tell me this guy's at what? 7.9 volts. So I know it's in the active region, right? You understand? Why do I know it's in the active region? It's between 1 volt and VCC. So we okay so far? So this is where we're sitting right here. We're sitting right here at 9 volts. So what we did is we brought in a 1 volt peak to peak waveform, right? Now, basically, and we'll talk about this later, we can calculate the gain of this by taking RC, which is equal to what? 10K, and we can divide that by RE, which is 1K. So I'm expecting our voltage gain, I'm anticipating a voltage gain equal to 10. So we can't bring a 1 volt peak to peak into the thing, can we? If I bring 1 volt peak to peak in, we should be getting what? 10 volts. Yeah, we can. It came from this voltage drop right here. So this guy's dropping 1.1. This guy's dropping 9. So VC voltage collector to emitter, according to Kirchhoff's law, would be the difference between those two, right? So what do I have on the collector? 9 volts. What do I have on the emitter? 1.1. So if I have 9 volts on one side of the resistor and 1.1 on the other side of the resistor, then we would subtract those two, and that would give us the voltage drop across that resistor. And guys, this is something you really need to learn. So back in DC, what did you do when you calculated voltage drops? Well, you measured across the resistor. In troubleshooting, we very seldom measure across things. We measure from common, right? You understand that. So what that does is get a circuit common. So what that does is it gives us the ability to take that black lead and put an alligator clip on it and clamp it on the common somewhere. And then now we're only probing with one lead, right? You understand? So what we're saying is if I've got a resistor right here, and in relative to common, which is what we're doing, I measure 9 volts on that side, and I measure 1.1 volts on that side, then how much is it going to be dropping? It's going to be dropping 7.9 volts relative to common. And that's what we're doing here, right? Y'all understand that? So all we did was figure out what VCE should be without actually measuring it. So I could come up here and put my meter right there and measure on that resistor, and I can measure that right there without trying to get my meter leads in across that transistor. Now, what's the problem with that? Huh? Have y'all seen these transistors? Have y'all seen these little transistors, how close those leads are together? So all it takes is you got your 2 meter leads down there, and you're looking over on your meter right there, and all it takes is just a little slip of your hand, right? You understand? And what did you do? You either shorted that thing emitter to base, or you shorted it base to collector. So you're shorting out 2 leads of the transistor, right? Which is going to cause, anytime we have a short, it could cause problems, right? You understand? I'm not saying it is, but it could cause problems. So here you're a troubleshooter, and you short out something and blow something up, and that's not what a troubleshooter is supposed to do. Your intent in life, it's like a doctor. You know, a doctor is supposed to do no harm, right? You understand? So you got a doctor that's killing people, then they're not going to be in business very long, right? So that doctor's supposed to not go in and cut something they're not supposed to cut, and we hear that all the time. You know, where before they started new procedures, where they'd cut off the wrong leg, cut off the good leg. So now what do? Yeah, they'll come in and right over the cut off this one, you know, when they come in and figure that out, so the doctors won't make a mistake, and then they still make mistakes, and then they still get sued, right? So what we can do now is I can come up here, now that I've got all these voltages, what can I do? I can take my meter lead and put it on this, and I can go here, I should expect 1.8 volts. I can measure right there, I should expect what? 9 volts. I can measure right there, I should expect around 1.1. And then I can calculate what VCE is supposed to be. And normally you can do that without a calculator, right? We can approximate that. So I wouldn't have to measure that 11 volts across RC. I've got 9 volts on one side, I got 20 volts on the other. I've calculated it's supposed to drop 11 volts. And so I got 20 volts on one side, 9 volts on the other. What's it dropping? 11 volts, right? You understand that? So you very seldom see troubleshooters that knows what they're doing trying to measure inside a circuit. So we're putting 1 volt peak to peak in. So this, what do we call this resistor right here? This is your temperature stabilizing resistor. What's this resistor preventing this thing from doing? It's preventing beta from changing. Because if beta tries to go up and this resistor tries to drop more voltage, it can't drop more voltage because why? It's got to drop 1.1. Why has it got to drop 1.1? Because this guy right here is dropping 1.8, right? You understand? So if current tries to go up, this base voltage does what? Goes down, the transistor cuts off a little bit. If it tries to go down, it tries to make this voltage less, which turns the transistor on more, which causes it to stay right at this voltage that we calculated, right? You understand? So this guy right here is designed, and that's what the feature of voltage divider bias. It's very stable over a wide range of temperatures. Not an infinite range, but over a wide range, right? You understand? But what we're going to do is we're going to see we sacrifice gain. But what it does is it allows my input signal can change the voltage. The bias is not going to change it, right? You understand? But if the input signal adds to it, then it's going to allow the base to go up by the same amount and vice versa. So 1 volt in. So what I'm going to do is I'm going to calculate VB max. And so we said this is going to be 1.8 plus 0.5. And then VB minimum. We really don't even have to do this, guys. But we'll do it anyway. Would be 1.8 minus what? 0.5. VE max is going to be 1.1 plus 0.5. This is the one that's important. And VE minimum is going to be equal to 1.1 minus 0.5. So this should go up to 1.6 volts, and it should go down to what? What's that? 0.6? Or 600 millivolts. I'm trying to figure out what we did wrong. So far, we're exactly where we was at, right? So IC max would be equal to 1K times 1.6 volts, which would be equal to 1.6 milliamp, right? And IC minimum should be equal to 1K I'm doing this, I'm not using, I'm giving y'all the wrong formula. The answer's right, but the formula's wrong. So I is equal to V, so this would be 1.6 divided by 1K, which would be 1.6 milliamps. So the answer was right, but the formula was wrong. If I change Ohm's law. So IC minimum would be equal to 0.6, right, or 600 milli divided by 1K, which should be what? 600 millivolt, 0.6, right? 1.6 and 0.6, and 600 microamps. Is that what we got a while ago? So VRC max should be equal to 10K times 1.6 milli, which would give us what? Would give us 16 volts, right? Okay. So VC minimum would be equal to 20 volts minus 16 volts, which would give us 4 volts. So if VRC goes up, then VC is going to go down, right? Y'all understand that? And VRC minimum is going to be equal to 10K times 600 microamps. VRC would be equal to what? Minimum would be equal to what? Six volts, right? Yes, no. 600 micros. What's that equal to? Six volts. So my output should drop down to so this right here would be 9 volts. This is 0. My output should drop down to 4 volts. And my output, oh, VC, so we didn't do VC. VC would be equal to 20 minus 6. So it should go up to 14 volts, right? Ah, that's perfect. So I don't know what we did wrong while ago. So what would be my peak to peak voltage? $14 minus 4. 14 minus 4. What would be? 14 minus 4. 10 volts. Which is what I expected. So what we can do to calculate gain, the output is developed across this resistor right here. Your input is across this resistor right here. You understand that? So what we can do, and I can show you how you can transpose this, but basically A, so in amplifiers, A stands for gain. And then D means it'll be what? Little b would mean a voltage gain. Will be equal to this resistor, which is 10K, divided by this resistor, which is 1K. And these cancel each other out. So my gain is going to be 10. A while ago I put volts, by the way, but gain has no units, it's a multiplier. So I brought 1 volt peak to peak in, and I got 10 volts peak to peak out, which is what we expect. So a while ago, I think I did this one right, but I think I didn't do this one right. When I just, instead of doing the math, I think I just drew it down.
Yeah,
Yeah, I know, which is wrong. So I knew it had to be wrong because I was expecting a gain of what? 10. Now this is unloaded. We'll talk about loading in a minute, but this is unloaded. Unloaded means I don't have a load out here. So normally, this load out here is going to act right now like a resistor. If we load that, if we load the amplifier, what would you expect the gain to do? Go up or go down? Yeah, we'd expect to go down. Now let's get it where we're at now, and then we'll figure out what's going to happen when we put a load out there. So we'll never have an amplifier without hooking up a load to it, right? So, all right, y'all, so take a break.